Hi everyone, welcome back to Chapter 3. And in this video, what we're going to do is we're going to talk a little bit about vector multiplication, and then we'll finish up the remaining time with a handful of example problems that I've chosen. And so getting through these example problems, it may or may not cause this video to run a little bit longer, but I figure you can stop the video and pick it up at a later time if you need to. But I want to keep all of the example problems together in one video set. And so in the previous video, we covered what was required to add and subtract vectors from one another. And one of the example problems that I have for later in this video will focus on that addition-subtraction method. But now we need to consider what it's going to take to multiply vectors together, or in this case, vector products. Now, as it turns out, there are two different ways that we can multiply vectors together. One way is to multiply the vectors so that we produce a scalar quantity. The other way that we can multiply vectors is to produce another vector. And so these two methods are what we call the scalar dot product and the vector cross product. Now, usually in a math class or some other class, these will be shortened down to just dot product and cross product. But the full name of each method, we have the scalar dot product and the vector cross product. And the reason I prefer to use the full name of these products is because we are reminded as to what we are going to produce. With the dot product, we're going to produce a scalar. And a scalar is just going to be a numerical value. We do not require any direction to be associated with it. But with the cross product, we are producing another vector, and so we have to have both magnitude and direction. So we'll go ahead and first of all define how we're going to represent these two types of products, because right now when it comes to showing the product of two values, say I want to take the product of A times B. Back in grade school or middle school, at first we were probably introduced to the X method for describing multiplication, and then by the time we got to like high school, that might have changed to a dot, and then eventually we just kind of abandoned both of those, and we said, well, if we just put the two letters together, that's understood to be a product. Well, now we're actually going to have to be very careful about what method of multiplication that we use, because each one of these is going to mean something different for us, at least in the case of vector multiplication. Well, as you can see right here, this second method of multiplication has a little dot between the two terms. And this is actually how we're going to denote a dot product between two vectors. So if we have vector A and vector B, we'll use the half arrow hat above those two vectors, and then to signify that we're going to take a dot product, we'll place a dot in between those two vectors. For a cross product, we're going to use the first notation. And so that x, if you were to turn your screen about 45 degrees in one direction, that X kind of looks like a cross, but it's sitting on its side. But that's going to be the notation that we use for our cross product. We should never see this third method when it comes to vector multiplication, because if I just have two vectors standing side by side, that may indicate a product, but it doesn't specify which of the two versions that we have to carry out. And that's kind of important because one version produces a scalar, the other version produces a vector, and the way that we produce the outcomes of these products is a little bit different for each. So we're not going to be using that last case scenario unless we are dealing just with the magnitudes of the vectors themselves. If you get rid of the direction aspect of the vector, then you're just working with magnitudes, you're just working with numbers. In that case, you can do regular algebra all day long. So next we need to look at how we're going to evaluate these vector multiplications. And I'm going to go ahead and show you the most basic approach for evaluating these products, but I'm not going to assign any homework on the vector multiplication. I'm also not going to have any problems on at the very least the first exam, because we're not going to need to use these vector multiplication methods until we get to chapter 7. And I feel that if we go over the material now and then we don't use it for another 5 chapters, I'm just going to have to come back and reteach the material again anyways. So let's just go ahead and save ourselves the time. We'll wait until we get to chapter 7 when we actually need this material, and then we'll step back to this chapter 3 content, and we'll learn the full content of the vector multiplication. But for right now, just in case you're interested, in order to evaluate a dot product, we will take the magnitude of each vector and we will multiply those together times the cosine of the angle that exists between the two vectors. So if we had vector A pointing here and vector B pointing here, so we'll say vector A is 8 meters at 20 degrees from the x-axis, and we'll say that vector B is 6 meters at 70 degrees from the x-axis. So right there I have everything that I need to evaluate a dot product between these two vectors. I know what the magnitudes of each vector are. I have 8 and 6. And then the angle that exists between them, so I need to know what this angle is between the two vectors. Well, that's just going to be the difference in their angles. B is at an angle of 70, A is at an angle of 20, so that gives me a difference of 50 degrees. So we have cosine of 50 degrees. We'll go ahead and plug all of that into our calculator. We have our 8 times our 6 times cosine of 50 and that's giving us approximately 30.9. And since we have units of meters over here, we'll have meters for the yep, okay. But the one thing that we're not going to have over here is any kind of angle value. And actually, I take that back. We had meters times meters, so that might have been meters squared. But there is no direction that goes with this value. It's just a number. It's just a scalar. Well, so now we want to see how are we going to evaluate the cross product. And it's very, very similar. We're going to take the magnitude of each vector times the sine of the angle between them. So again, we have our magnitudes of 8 and 6, but now we're taking the sine of 50 as opposed to the cosine. And I'm getting 36.8. Now again, the units would be meters squared because I had meters for vector A, meters for vector B. But now, because this is a cross product, maybe we could call this combination vector C, because our cross product will produce another vector. Vector C has a magnitude of 36.8 meters squared, but now I need a direction for that vector to point. And as it turns out, and you'll learn a method to prove this in Calc 3, but anytime you take a cross product, the resulting vector will be perpendicular to the original two vectors that you used. This does not mean that vector A and vector B have to be perpendicular to each other. In fact, they're not, because right there, that was the angle between the two vectors. So this is not a requirement. That's not to say that it couldn't happen. You could have an angle of 90 degrees between the two vectors, but that would just mean that you have sine of 90. Sine of 90 is 1, and then you would just get the combination of the two magnitudes. All right, so we will continue discussing the dot product in Chapter 7, because when we get to Chapter 7, we're going to start talking about work and energy, and those two expressions are scalars, but we need to evaluate the work that is done from vector quantities. And so that's why we're going to need to use the dot product. The cross product, we're actually not going to see that until Chapter 10, which is at the very end of the semester. But we'll go ahead and review the cross product there. But then we're going to see both the dot product and the cross product show up quite frequently in Physics 2. So if you have to take Physics 2, we'll be getting even more exposure to this dot product and cross product method. So now, moving on, I have 4 example problems with vectors that I would like to show you. And the first one will be more of a hypothetical vector problem. We know now that when it comes to adding vectors together, we have to add them head to tail. But let's assume that we have a vector. Let's try something other than A, B, C, or D. Let's try vector F. Vector F has a magnitude of 13 meters. And vector G has a magnitude of 8 meters. And we want to add, sorry, I'm still stuck on ABC. We want to add the two vectors together to produce a resultant vector. And I'm going to give you a handful of choices. Let's see, we'll do A is 0, 4, 12, let's see what else we want. We'll do 22 and 25. Okay. So we want to add vector F to vector G to produce vector R. Which of the following choices, so what could be the magnitude of vector R? So I want you to add vector F to vector G and tell me which of these could be the resulting magnitude of their combination. Now the one thing that you should be questioning here is what direction are these vectors pointing in? Because all I gave you were the magnitudes. I gave you vector F, which is 13 meters long, and I gave you vector G, which is 8 meters long, but I didn't tell you what direction those vectors were pointing in. And every vector has to have those two pieces of information. We have to have magnitude and direction. And so I'm asking you to add together two terms while missing some very important information, because in the previous examples of adding together vectors, if vectors were pointing in two directions, then we would have to break them up into components so that we could add together components and find the components of the resultant vector. So in other words, I would need to know the x components of the two vectors so that I could find the x component of my resultant. I would need to know the y components of my vectors so that I could find the y component of the resultant. And then I could put these together with my magnitude mantra to find the magnitude of the resultant vector itself. Well, so how am I supposed to do all of that if I don't know where these vectors are pointing? And that's why this is more of a hypothetical question than anything else. What we need to do to answer this is we need to consider all possibilities. What are all of the possible ways that these vectors could be combined? So let's start with the most extreme case. What if we added these vectors together, head to tail, in a straight line? In that case, we would produce a resultant vector of 21 meters. And no matter how I try, I cannot produce anything larger than that. 21 is going to be the absolute largest magnitude that I can produce for any combination of these two vectors, because after this I have to start introducing some amount of angle to the vectors, which is going to cause the resultant vector to actually start shrinking in size. Eventually, we will get our two vectors at a 90-degree angle, and at that point we can actually use the Pythagorean theorem to tell us what the resultant should be. So we would have 13 squared plus 8 squared, and we square root that, and we get this hypotenuse would be about 15.3. But up here, if we wanted to find the value of the resultant, we would have to use something like law of cosines or law of sines in order to figure out what that resultant value is. But believe me when I say that this value of r is going to be less than 21. And then as we continue changing the angle, our r value gets even smaller until we get to the other extreme, which is to add the vectors in an anti-parallel arrangement. So we do still have them added head to tail, but our resultant vector is always drawn from the start to the end point of our vector addition. So when I travel out on the 13 meter vector and then I backtrack 8 meters, well, I've only got 5 meters left. And so it turns out that 5 meters is the absolute smallest vector that I can possibly produce. And it's at this point that someone says, well, you told us that it doesn't matter what order we add the vectors together. What if instead of starting with the 13, we started with the 8? Okay, well, in the first extreme case, 8 and 13 added one after the other in the same direction is still 21, but 8 and in this case negative 13, we would add a negative vector that still has a magnitude of 13. This is going to result in a vector of negative 5. But what's the magnitude? Haha. The magnitude of that resultant vector is still 5. And so whether we're adding 13 to negative 8 or 8 to negative 13, the resulting value of that is still a magnitude of 5. And so our resultant vector is going to have a range of values that exists between those two extremes. We cannot have anything less than 5. We cannot have anything greater than 21. And so now we can see quite easily what the answer is. The only valid answer that exists within this range is 12. Now, how do I arrange these two vectors in such a way that I'm going to get a resultant of 12 meters? Well, I don't know what the exact angle relationship is going to be, but it's probably something like this combination right here. And again, for something like this, we would probably have to use something like law of cosines or law of sines to figure out exactly what the angle relationship would be, but it is a possible combination. So that's the first example problem. As I said, hypothetical. This is testing our understanding as to what is possible for a vector combination. We cannot just produce any value that we want. There is a physical range that limits our possible answers. So now moving on, for our next example problem, I have 4 different vectors, and we'll go back to the A, B, C, D. So we have 4 different vectors, and I am going to describe each vector in a different format. Vector A, I will describe in component form. So vector A has x and y components 6 and 10. And we'll let all of our vectors be in meters. Vector B, I will describe using magnitude and direction. So vector B is 8 meters long, as measured 120 degrees from the positive y-axis. Vector C will also be in magnitude and direction, except that the direction that I'm going to use is a compass direction. So vector C is 12 meters, measured 35 degrees south of west. And then vector D will be 5 meters at 3/2 pi radians. We've been using degrees for our angle measurements, but another possible unit for angle measurements are radians. And so if you remember from your days back in trig, pi is equal to 180 degrees. And so we can use this ratio of pi over 180 as a unit conservation. Whether we have pi over 180 or 180 over pi, either way the ratio is still 1. But that means I should be able to convert that 3/2 pi into an angle. And you'll notice here I did not specify where that angle should be measured from. And if that ever happens, then by default we are supposed to measure from the positive x-axis. So we have here 4 different vectors. They're all being described in different ways, but they're all valid descriptions of a vector. The next thing that we want to do is we want to produce a combination of these vectors. And we might as well start with something basic like a plus b plus c plus d equals vector r. So I want to know, what is vector r? I want to know everything about vector r. I want the components of vector r, I want the magnitude of vector r, I want the direction that vector r is pointing in. So to do that, my best option is to get all of these vectors in the same format so that they can be combined in the same format. Well, I have 4 different formats here. I have components, I have magnitude and angle, I have magnitude and angle on a compass, and I have magnitude and angle using radians. And I've said it multiple times already, but the best approach for combining vectors is components. And so I am going to take the time to convert all of my vectors into component form. A is already in component form, so it's ready to go. But I have to figure out what are the x and y components of the other three vectors. So I'll go ahead and start with vector B, and I will make a quick sketch of vector B just so I can see what it looks like, and then I will apply the trig to produce the components of vector B. So vector B is 8 meters long, and we have to measure 120 degrees from the positive y-axis. And that 120 degrees is positive, so that means we have to measure in the positive direction, and that's the counterclockwise direction. So I measure 90 degrees, and so now I'm at the negative x-axis, but I have to keep going an additional 30 degrees past that. So that's 120 degrees from the positive y-axis. Turns out my vector B is down in the third quadrant, and that means that both the x and y components are going to have to be negatives. And it would be a good thing to probably remind ourselves. I'll go ahead and put the necessary sign notations up there next to the x and y components. And now we have to figure out how do we take that 8-meter magnitude and get the components out of this, especially since the angle that we were given is bigger than 90 degrees. I can't fit an angle larger than 90 degrees into a right triangle, and I need a right triangle to use the trig to give me the components that I need. Well, let's just go ahead and sketch what those components need to look like. I need one component in the x direction, b of x, and I need one component in the y direction, b of y. I now have a right triangle which is using this much of an angle, and that angle phi, well, that's just the difference in the 120 and the 90 degrees between the y and the negative x-axis. So phi is the difference between 120 and 90 for 30 degrees. So I can use phi inside of that right triangle to tell me what the x and y components of my vector are. And then I already have my reminder up here that says that those components both have to be negative. And we can see that in the picture. We can see that both of those components are pointing in the negative x direction and the negative y direction. Okay, here we go. B of x, that is the leg that is adjacent to our angle, so that will be cosine of 30 degrees. B of y is the leg opposite of our angle, so that is sine 30 degrees. The values that we get for those are, this would be 4, and I'll have to put cosine 30 into my calculator there. 8 cosine 30. .93, and everything that we had was originally in meters, so our components will also be in meters. Negative 6.93 and negative 4. Those are the components of vector B. On to vector C. Vector C is 12 meters, measured 35 degrees south of west. So when it comes to our angle measures, we can still use positive x, positive y, negative x, negative y, but those axes now have to be related to the respective compass directions. And the way that we're going to read these compass directions, we actually kind of have to read them backwards, because we are measuring south of the west axis. We are measuring south of west. So that means we have to start from the west axis and we have to measure to the south. And we have to measure that 35 degrees. And so vector C is almost right on top of vector B. Vector B was 30 degrees below the negative x-axis. Well, vector C is 35 degrees below that axis. So just like vector B, vector C is going to have two negative components. Vector C is in the third quadrant. It's going to have two negative components. So we'll find out what those are. We have an x component and a y component. X component will be magnitude. C has a magnitude of 12 meters. And our x component is the leg adjacent to our angle, so that is cosine. And that means our y component will be using sine. Calculator time, 12 cosine of 35, 9.83, and 12 sine of 35. 6.88. And these are both negatives, so when we plug them in up here, I don't know why I have that taskbar there, but 9.83, there, went away, 6.88. Okay, one more vector. We need to take vector D, convert it into its components. And then once we have those components, not only will we be set up to do this particular combination of the vectors, but I can then go through and I can change any of the vectors to a negative very easily and produce a new resultant. But for right now, let's just focus on getting vector D. So I'll make myself some room here. The first thing that we probably want to do is convert our angle from radians to degrees. So we're starting here with 3/2 pi radians. And we saw up above that we can use 180 over pi as our conversion factor. So we'll get our little goalpost out for unit conversion. And I want to get rid of the radians. So we're putting pi radians in the denominator, and we want to replace the radians with degrees. So the 180 goes in the top. We now multiply across the top and the bottom. So we have 3 pi times 180 over 2 pi. The pi's will cancel out. The 2 and the 180 will reduce to 90 and a 1, and so what we have here is 3 times 90, or 270 degrees. In other words, vector D is pointing right along the negative y-axis. So vector D is all in the negative y direction, which means we do not have an x component, and the entire magnitude of that vector has to be in the y direction, but it has to be negative because we're pointing in the negative y direction. Okay, we're ready. We can now do any combination of these vectors that we can dream up. Let's see, technically there would be, I think, 8 different possible combinations of combining these vectors just by switching out the plus and minus signs in the front. But right now we're taking vector A plus vector B plus vector C plus vector D equals vector R. So we'll just go right down the columns here. All we have to do now is add up the x components of our vectors as they are, and we will produce the x component of the resultant vector. So we have 6 plus a negative 6.93 plus a negative 9.83 plus 0 makes negative 10.76. That is the x component of our resultant vector. The y component, we'll get that from adding all the y components together. We have 10 plus a negative 4 plus a negative 6.88 plus a negative 5. And that gives us a negative 5.88. And in all honesty, we're really done with the problem. Even though I said I want to know the magnitude and direction of vector R, well, we can get those quite easily just by using the components. The magnitude of our vector is the square root of the sum of the squares. You have 2 negative quantities that are being squared. You will lose those negatives. And we're going to end up with something close to the square root of 150. And so after we take our square root, we get approximately 12.26 meters. So everything over here is still in the units of meters. And the direction that our resultant vector is pointing. If we look at the components, both of the components are negative. That means that vector R has to be somewhere in the third quadrant. We will plug those values into our inverse tangent. Inverse tangent says R of y over R of x. So if we want to stick with the theme here, it's going to be the y component over the x component. But when we do this, we have 2 negatives that, well, those negatives are going to drop out. And so when we plug this into our calculator is going to give us a positive angle measure. The 5.88 over 10.76, we need an inverse tangent of that, and I'm getting 28.7 degrees. And the big question now is, where do I have to measure that angle from? And in the previous video, I said keep an eye on what is in your denominator, because whatever component is in your denominator, that is the axes that you need to measure from. In our case, we had a negative x component. And that means that this angle will have to be measured from the negative x-axis. Well, there's my resultant vector. There's the negative x-axis. Does that angle measure look like it might be 28.7 degrees? Especially if you don't do a freehand sketch here. If you actually come out the negative 10.76 and then drop down the negative 5.88. Does that angle look like it might be about 30 degrees? And even with my rough hand sketch, that looks pretty convincing. But now, as I said, we have these 4 vectors. We can pretty much do whatever we want with them. I could very easily come in here and say, well, I don't want a plus b plus c plus d anymore. I want come on, switch over. I want a plus b minus c plus d. Now I've thrown some parentheses in there to kind of throw you, but the parentheses, those are just part of the order of operations. The parentheses say, you know, we need to add a and b together, we need to add c and d together, and then we need to take the difference in the answers. Well, that could be a bit more work than what we really need to do. Instead of following the order of operations, what if we removed those parentheses? I mean, a plus b inside the parentheses, that's still just a plus b. But then if you subtract the quantity c plus d, isn't that really just the same as subtracting c and subtracting d? And the answer is yes. And so now I don't actually have to go through the order of operations. I can just perform a vector addition problem using negative vectors. All I need to do now is I need to convert vector c and vector d into their negative counterparts. And that's very easy to do now. We saw in the last video, all we have to do is throw a negative sign in front of c, and what we do to one side we have to do to the other. So if I'm going to change the sign on the left, then I have to change the sign of everything on the right. And so carrying a negative sign through is going to change those negatives into positives. Likewise, I need to put a negative sign in front of D, which means I need a negative sign in front of everything else. Technically, there's no such thing as a negative 0, but we do end up changing the negative 5 to a positive 5. And now I'm ready to add everything together. I'm ready to get an answer for this combination. We'll go down the columns. We'll add all the components as they are. We have 6 plus negative 6.93 plus 9.83 plus 0 makes for, and I'm going to call this resultant 2, because this is going to be different from the previous resultant. I have a positive 8.9 for my I-hat. And then we'll go down the y column, adding the components as they are. 10 plus negative 4 plus 6.88 plus 5 makes for 17.88. And so R2 is a first quadrant vector. I can tell that just by looking at the signs on the components. And now if I need to know the magnitude of R2, I can plug that into the square root of the sum of the squares. If I need to know the angle for R2, I'll call that theta 2. I can plug that into my inverse tangent. I'm working with a positive x component here, which means my angle will be measured from the positive x-axis, just as I've drawn it here. All right, so as I said, there should be about 8 different combinations of how you can combine vectors A, B, C, D just by switching out the plus and minus signs. I'm going to do one more example with these vectors. So I'll get rid of this stuff here. And I also want to return all of my vectors back to their original form. So I want to take vector negative c, turn it back into just regular vector c. So to do that, I'll factor out the minus sign from all of the terms. So now we're back to the original vector c. I also want to revert back to the original vector d, so I'll factor out the minus signs on those. Those are the 4 original vectors. And I'll just throw a combination up here, negative a plus b minus c plus d minus e equals 0. So now we have a 5th vector. A vector that I don't even know what it is. But in this particular combination, those vectors all add up to 0. And I want to know, what are the components of vector E? So what are the x and y components of vector E? Well, it's actually a very straightforward algebraic expression. I'm trying to get E to equal something, so why don't we go back up? Sorry, I forgot some of my arrowheads there. Why don't we just go back up to this top equation and move our E vector over to the other side. And once we do that, well, I now have an algebraic expression that tells me what vector E has to equal. And now, well, that's not hard. All I have to do is come back to my collection of vectors here. I need the vector negative a, so I'll take vector a and I'll turn it into vector negative a. B can stay the way it is. Vector c, well, I need to turn that back into vector negative c. And vector d can stay the way it is. So this combination of vectors added together will produce vector E. We're now ready to add down the columns using the components as they are. We have negative 6 plus negative 6.93 plus 9.83 makes for a negative 3.1 I hat. Then we'll go down the y column. We have a negative 10 plus a negative 4 plus a 6.88 plus a negative 5 makes for negative 12.12. So those are the values of vector E. And just in case we were curious, do we have the correct answer? Does this combination equal 0? Well, let's come back down to our vector collection here. And now that we know what vector E is, let's add that, or rather its negative, to the vector addition problem. So we now need to add the vector negative E. So I need to take vector E, I need to turn it into negative E. And now if you go down the columns and you add everything together, well, it's no surprise that both of those columns are adding up to 0, which is what we're expecting for the resultant of this vector combination. Okay, so that's the second example problem. Granted, it was pretty involved, but there are a lot of different ways that we can apply that knowledge to some vector addition and subtraction problems. So I think that one was worth having as one of our example problems. The next example problem that we'll do, this one is more of a concept check as opposed to a physics problem. We're going to have two vectors, vector C and vector D. We're going to add those together to make vector E. Now, we are told what the components for vector C are. We have 6 in the I hat, negative 8 in the j hat, and we'll go ahead and use meters for these units. We do not know either component for vector D, but we do know that vector E is only in the x direction and has the same magnitude as vector C. So, what is vector D? What are the components of vector D? That is the question. Now up here, these are all the clues that we've been given to sort of fill in the gaps here, because right now I have technically 4 unknown values. Now I'm going to go ahead and set this up with the column approach that we've been using before. So I know vector C, I don't know either of the values of vector D, and then vector E, we're given 2 pieces of information. We're told that vector E is only in the x direction, which means that if we're only in the x direction, we cannot have a y component. So the y component of vector E has to be 0. If that is the case, then whatever the y component of vector D, it has to combine with the y component of vector C to produce that 0 for vector E. Well, we know what the y component of vector C is. It's 8. Or excuse me, it's negative 8. So negative 8 plus something has to equal 0. Well, that's kind of a no-brainer. We need a positive 8 there. So we've got half our answer. We now know the y component of vector d. But the x component of vector e is not 0. The other clue they gave us is that vector e has to have the same magnitude as vector c. So let's take a moment and find out what is the magnitude of vector c. Magnitude mantra says square root of the sum of the squares. And as we put all that into our calculator, it turns out that the magnitude of vector c is equal to 10. Magnitude of vector c has to equal magnitude of vector e. Well, the magnitude of vector e would be the square root of the sum of the squares of the components of vector e, except that vector e has a y component that is equal to 0. And if that's the case, then, well, that means that the magnitude of vector e just has to equal the square root of the x component squared, or the magnitude of vector e is just going to come from its x component. Well, okay, if vector c has a magnitude of 10, that means that vector e has to have a magnitude of 10, but we now know that vector e is going to get its magnitude from its x component. So there's our x component for vector e. The x component for vector e is produced by taking the combination of the x components of vectors c and d. And so we have a x component of 6 plus something equals 10. The only way that's going to happen is if d has an x component of 4. And now we're done. We have the components of vector d. From there we can find magnitude and angle if we're asked for it. But we're at the end of the problem. So that was a slightly shorter example problem. But now we'll finish off with a slightly more complex example problem. So this will be the last example problem for this video, and then we'll actually call it good for chapter 3, because we have everything that we need to know, minus the vector multiplication stuff, which we will cover in future chapters. All right, so now we have vector A, which is actually unknown to us. Once again, we'll go with meters. And vector B is also unknown to us. However, we know that if we take 2 times the value of vector A and add it to 3 times the value of vector B, we will get values of negative 9 I hat plus 16 j hat. And if we take 3 times the value of vector A minus 5 times the value of vector B, we will get 34 I hat minus 28 j hat. So given this information of these 2 different combinations of the vectors, we want to find the individual components of vector A and vector B. So what we have in front of us here is a system of equations where we have two unknown quantities. Vector A and vector B are the unknown quantities. And so what we have in front of us are two equations with two unknowns. And typically, as long as you have the same amount of equations as you have unknowns, then that system can be solved. The question is, how are you going to solve it, especially since we have everything in vector form now? Well, we're actually going to solve this using the same algebraic methods that we would use for any other system of equations. I know that I have scalar multiples of my vectors in these equations, and then when they get added together, they're like terms, hence all the i's will combine and all of the j's will combine. So what I want to do is I want to see if maybe I can do a combination of these equations in such a way that I can eliminate one of the unknown variables. And what I want to bring your attention to right now is this symbol right here, this equal sign. And this says I have to have the same stuff on the right side of the equation as what I have on the left side. Likewise for this equation. Well, if I were to combine everything on the right-hand side, would that equal the combination of everything on the left-hand side? And the answer is yes, it has to. But if I combine everything on the left-hand side, I'm not going to eliminate one of those unknowns. If I add the two left-hand expressions together, I would get, what is that, 5a minus 2b, and then that would equal whatever combination I got from adding the i's and j's on that side. So I would just be producing a third equation with stuff that I can't solve. So I need to get a little more inventive with this. I need to figure out a way of eliminating one of those unknown variables. And if you've been in a college algebra course before, you've done this. First, we need to basically just pick one of the two unknowns that we want to eliminate. And so I'm gonna choose A. I want to eliminate A from this system of equations. And to do that, I need to get the same coefficient in front of my A for each of those equations. And the easiest way to do that is to just take the current coefficients and multiply each line by the coefficient of the other equation. Now that might not make a whole lot of sense when I say it out loud, but it will make sense when I write it down. Right now I have a coefficient of 2 and a coefficient of 3 on my A terms. Really what I'm looking for is a common multiple of those two values, and the least common multiple of 2 and 3 is 6. So how do I take that top equation and turn the 2 into a 6? Well, I need to multiply it by a 3. How do I take the bottom equation and turn that 3 into a 6? Well, I need to multiply it by a 2. So there is the statement that I just said. We're gonna take each line and multiply it by the coefficient of the other. But I have to multiply both sides of those equations by those coefficients. So over here, we're going to distribute the 3 through that top equation, and when we do that, we get 6a plus 9b equals negative 27i hat plus, and I think this is 48 j hat. So there is the top equation, and because I've multiplied both sides of the equation by 3, I have not changed the equation. We could just as easily go back through and factor out the 3's, but I'm gonna leave it alone for right now, because now we're going to factor the 2 through the bottom equation, which will give us 6a minus 10b equals 68i minus 56j. And what we can do now is we can actually combine these two equations in such a way that we can eliminate the a from this system of equations. And the way I will have to do that is I will have to subtract one equation from the other, because right now both of my a terms are positive. So I am going to subtract the bottom equation from the top equation. When I do that, 6a minus 6a is 0, so all of the a terms are gone. 9b minus a negative 10b. Careful with your algebra here. 9b minus a negative 10, that becomes a positive 19b. We have 27, negative 27 minus 68, and that gives us a negative 95 I hat. We have 48 minus a negative 56, so that's actually 48 plus 56, 104. And now all that's left is an equation that has one unknown term in it, and that unknown term is b. Now we've already seen that vector multiplication with scalars, all that does is it carries the scalar through the components. So what would vector division do? Well, division is really just multiplying by a fraction, and so if we came through here and we multiplied everything by 1 over 19, then we will get the values of the components of vector b. So we have negative 95 divided by 19, and I'm getting negative 5. And then we have 104 divided by 19, which is 5.47. And right now I can see that I'm not going to be getting the values that I was supposed to get, so I need to double check and make sure that I did everything correct with my values. Otherwise we can continue through and see what new solutions we get. But right now I just want to double check, make sure I had everything correct. So 2a plus 3b, 3a minus 5b. So it looks like everything is correct. Double check my multiplication here. 6a, 9b, 27. 3 times 16 is 48, that's right. $34 and 2 is 68. 28 and 2 is 56. So now we'll check my subtraction. 9 and 10, negative 27, negative 9, 5, yep. 48. Oh, looks like all my math is correct, so maybe my original solution was incorrect. Oh, this just means that we're going to get some decimal solutions. So hopefully we don't get something impossible in terms of our answer. But we'll keep going here. We're committed now. So I have my components for vector B. I'm halfway done. And you would think that now that you have the components for vector B, you could plug those into the two equations down below and then use vector B as a substitution to solve for vector A. But again, that is assuming that your answer is correct. That's assuming that your components for vector B are correct. If they're not correct, then you're running the risk of getting the wrong answer for A by using the wrong answer for B. So instead, you'll notice we were able to get an answer for B independent of A. So let's try getting an answer for A independent of B. So now we're going to go back to the original set of equations, and we want to eliminate the B's from these expressions. And the easiest way to do that is to find the least common multiple for the B terms. For 3 and 5, that's a 15, so we need to multiply by 5 and 3 respectively. Our top equation, when we carry the 5 through, we will get 10a, 15b, minus 45 I hat, plus 80 j hat. And then for the bottom equation, we're going to carry through the 3, which gives us 9a. We have a minus 15b equals, and 34 times 3 is going to make for 102 I hat. 28 times 3 is going to make for 84, and that is a negative. And now we need to combine these equations to eliminate the b's. Well, the b in the top expression is positive, the b in the bottom expression is negative, and so all I need to do is just add the two equations together. 10a and 9a is 19a, 15b and negative 15 is 0, negative 45 and 102 is positive 57, and then we have 80 and negative 84, which is negative 4. Alright, so we're We're also not going to get the best answers for this either, but just like before, we will divide through so that we get A by itself. 57 divided by 19 is 3. And we have a negative 4 divided by 19, which is negative 0.2105. I'll just round that up to 1. And so these are the answers that we have. So again, I apologize for not starting off with the correct solution, but this is often something that's going to happen in your real work, is that you'll have solutions that are not quite so pretty, especially if you get to go on to linear algebra. Linear algebra is going to be all about solving systems of equations like what we have here. And so now comes the point where we want to check our answers, and we want to see if these answers are in fact valid. And the way that we can do that is we take our two answers and we plug them back into one of the original expressions. And now is where I'll see if I made any critical errors. But we have 2 times the value of vector A. So 2 times the value of vector A would be 6 I hat minus 0.422 j hat. And then we have to add to that 3 times the value of vector B. So 3 times the value of vector B is negative 15 I hat plus 3 times 5.47, which is 16.41. And so if we add those together, we have 6 and negative 15 makes for negative 9. And then we have a negative 0.422 and a positive 16.41, which gives us approximately exactly what I need. So I'm gonna go ahead and assume that I have the right answers here, just because with my decimal values, I had to cut off those decimal values at some point. If I had carried out those decimal values even further, I would have gotten even closer to the correct value of 16 here. But I'm only off about 1/100th of a decimal point there, and so I am in fact getting the correct outcome for the first combination of those vectors. And so now I can double check my solutions by plugging them into the second set of equations. But at this point, I don't know if I want to push my luck, but I probably wouldn't be doing my job unless I plugged everything in as is. So I need 3 times the value of vector A, which is going to be 9i minus 0.633. And we have to subtract 5 times the value of vector B. Vector B. Oh, come on, vector B. So negative 5 times the values of vector B. So negative 5 times negative 5 is 25. And then I need -5 times 5.47, which will be -27.35. And so everything can now be combined. Write down the columns. 9 and 25 is going to make for 34. I hat. And then we have a -27.35 and a -0.633, which again, we're within about a hundredth of a decimal place, which is giving us a -28 j hat, which is also what we need. And so, even though I screwed up my own solution, we were still able to get a real solution. So that's a relief. But this is actually probably a good thing, because even though I tried to set up a system of equations that would have nice integer solutions, those integer solutions are probably not going to be that realistic for a real-world problem. Okay, so this brings us to the end of our Chapter 3 material. Now that we have all of this knowledge about vectors, we know how to take a vector, break it up into its components, we know how to put those components back together, and we now know how to add and subtract vectors. We need to take all of this knowledge from Chapter 3 and plug it into the knowledge that we had from Chapter 2, specifically with any of these kinematic terms which happen to be a vector. And as it turned out, the first 4 of these terms are vectors. Displacement is a vector, our velocities are vectors, our acceleration is a vector. The only one that is not a vector is time. And so now if we go back to Chapter 2 and we look at those 5 kinematic equations, every one of those equations is going to get a whole bunch of little arrow hats distributed through the terms that are vectors. And we now need to figure out how we're going to basically navigate the math in these kinematic equations if we're working in 2 or 3 directions at the same time. And the way we're going to do that, and the way we're going to make our lives a little bit easier, is we're going to use the idea of vector components so that we can work in one direction at a time. So we're actually gonna take these kinematic equations and we're gonna break them up into a system of one-dimensional problems. And so the next video in line will be part 1 of Chapter 4. See you then.